Here's a good question about work and energy. The cyclist starting from rest, freewheeling down a hill, and after a bit the road becomes horizontal, and then the cyclist stops. Now, as with all mechanics questions, a good diagram is essential. So there's a cyclist. The cyclist has mass 70 kilograms. So we can resolve this into the slope. So that's 70g cos 20, and this is 70g sine 20. There's obviously a normal reaction, and there's also the resistance, which we'll call R. Now, by the time the cyclist gets to the bottom of the slope, she's done two things. Firstly, she's now got some kinetic energy. She had no kinetic energy at the start because she started from rest, it says so up here. And then she's also done work against this resistance. Now, how has she managed to gain kinetic energy and do this work against this resistance? Is because initially she had some potential energy. So the conservation of mechanical energy states that these two must be equal. So the initial potential energy is going to be 70 g, and then the height is 60 sine 20. But we know the distance is 60, so 60 sine 20 is the height. So the potential energy is mgh. And then the kinetic energy is obviously a half mv squared, and we don't know what v is. And the work done is the force multiplied by the distance. So just to reiterate, this gain in kinetic energy and the ability to overcome the resistance is only possible because she had some initial potential energy. So on this slide I've just written out the formula again. 70g times 60 times sine 20 works out to be 14077. Half of 70 is 35, and that's 60. So v squared is 14077 minus 60r all over 35. So that's the first stage of the journey. So here's the question again. So we've done the first bit, but then the road becomes horizontal and the cyclist travels a further 50 metres before coming to rest. So let's draw a diagram. Here's the cyclist. There's still the resistance. She's moving in this direction. So the only force acting on the cyclist is the resistance R. So Newton's second law tells us that R, that's force, is mass 70 multiplied by the acceleration. Clearly it's a deceleration because the cyclist is slowing down. We can now use SUVAT on this system. So A from here, A is R divided by 70. The distance travelled we know is 50, tells us here. Now a bit confusing with the U's and the V's. The U is the initial velocity in this second part, so that's what we had up here, which we called V. It was the final velocity of the first part, is the initial velocity of the second part, and then comes to rest, so the final velocity is 0. We're not interested in t, so we can use the SUVAT equation that doesn't have t in it, which is v squared equals u squared plus 2as. So naught equals v squared minus 2r over 70 times 50. just to try and reiterate this slight confusion about the U's and the V's, there's two parts to this. At the end of the part where she's coming downhill, we've called that V, so that's the end of the first part, so that V is the start of the second part over here, so that's why U is V and why we've got that bit here. So from this equation here we can say that V squared is 2r times 50 over 70, 2 times 50 is 100, so it's 10/7 of r. And we can now substitute equation 2 into equation 1 to work out what r is. So now it's just algebraic manipulation. Here's the two equations, so I can say that 10r over 7 is 14077 minus 60r over 35. You can probably do the rest of this yourself. We get 350r, and now we have to do 7 times 14077, so that's 98539, minus 7 times 60, that's 420r, so 770r is 98539, and that means that r is 127.97, which is 130 newtons to 2 sig figs. Since we used G in the calculations, we should give 2 sig figs,